Hi, everyone. This session is going to deal with the paper that was set by the South African Mathematics Foundation in the year 2025. This is the round 3 of the senior paper. So there are 6 questions, and this is the last round of each of the SAMO competitions they have, and is traditionally the most difficult one. So we will go ahead with trying to unpack the solutions of these 6 problems. These problems can be found together with the solutions in the SAMO website, which is www.samf.ac.za. The solutions are very scant in that, and we hope that this presentation will unpack that so that the solutions become very much clearer. Okay, so let's go ahead and get to the first problem. This problem says that the 4-digit number 2025 has a property that the sum of its digits is divisible by 9, which makes the entire number divisible by 9. It is a test for divisibility. You add all the digits, that sum is divisible by 9. The original number is divisible by 9. This particular number has got exactly one of the 4 digits, 0, but not the first one, obviously. It's a 4-digit number. The question is, how many 4-digit numbers have this property? All right, so let's have a look at this. So we have to fill in three blocks here with the 0. The 0 can't occupy the first position because it's a 4-digit number. So the 0 can occur here, here, or here. Okay, let's take any one of the situations and we will count. Suppose we look at just this one here. Okay, now we count how many numbers with a 0 in the second place make the sum of the digits is divisible by 9. Right? The sum of the digits of that number must be divisible by 9. All right, now, for it to be divisible by 9, the sum of these 3 digits must be a multiple of 9. Now, just observe that no matter which 2 numbers you put in here, like for instance, suppose I put say 5 and 6, right? Then this third number is automatically, you got 11, and so you have to have the digits to add up to 18. So third number can be only 7. If I had the digits to be 1, 4, I'm talking about the third and the fourth, then this is forced to be 4. So no matter which 2 digits you have, right, 8, 9, then this is supposed to be 1. This is 17 plus 1. So in other words, I only need to put any 2 digits in the third and the fourth position. And then there will be only one way in which I can make this entire number to be divisible by 9. Okay, so you can put whatever you like here. And then there will be one number that can be put in there. So the number of ways, the number of such numbers is equal to the number of ways in which the last two digits can be chosen. Okay. So now let's choose this digit. How many ways can you choose the third digit? You're not allowed to choose a 0, but you can choose any one of 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the third digit can be chosen in any one of 9 ways. And once the third digit is chosen, then the fourth digit can also be chosen in any one of 9 ways. You're allowed to repeat. You could have had 4, 4, for instance. So the fourth digits can be chosen in any one of 9 ways. And so this is equal to 9 times 9. Right? That's 81. Okay, now this is when the second digit is 0. Then for this particular one, you got 81. And if the second digit, if the third digit was 0 instead of the second digit, then you'll have another 81 there. And the same applies to the fourth digits. Another 81 and another 81. Yeah, so it's 81 times 3. So that's the answer. So there are 243 such numbers. Okay. I always have the actual solution, the type solution, um, like today, and I'm going to expose this type solution to you so that you can see the full solution. All right, the way it's supposed to be written. And here I've actually listed all the 243 numbers, counted them, and you can have a look at that. Okay, the second problem is a sequence of letters where each letter is either A, B, C, or D is called alternating if between any two A's there is at least one B. Let's just we'll put this sequence in a box again. 6 numbers. Why? Okay, so you got the 6 numbers A, B. They chose from A, B, C, and D. Hmm. Sorry, this is quite a mess here. I should have been. All right. So you got the not numbers, letters, A, B, C, D. You can put them anywhere, but there are conditions. The conditions are that between any two A's, there's a B. So you have A and A, at least one B. So they don't have to be only two units apart. If you've got two A's, there must be at least one B here. All right. And then between any two B's, there is at least one A. So I could have put a B here, but I can't put a B here because there must be at least one A. Can't put a B here. So this is the only place where I can put a B here in this case. All right. And between any two C's, there is at least one D. You can't put the two C's here. So you can't put the two C's here. The only way you could put the two C's is here, and you have to put a D there. So this is an example. And between two D's, there is at least one C. Okay, now the question is calculate the number of alternating sequences of length 6. Yeah, I already anticipated that the length is going to be 6 here. And this is an example of such an arrangement. Okay. So now the question is, how do you count this? How many are there? Okay, let's just see. Let's figure out a strategy of counting this thing. Let's separate it. Very often you separate the smaller pieces and then count it, and get to the next piece, count it. As long as these different pieces they don't have anything in common. Like in this case, if we say, okay, let's say how many A's are there in this? You got 6 slots, right? It's quite possible you have no A's at all. You've only put B's, C's, and D's. But you can, how many A's are there? Well, obviously, you can't have 6 A's because you need to have at least one B. You can't even have 4 A's because you need to put a B here, you have to put a B here, and put a B in between. So, and you only have 6 slots. So 4 A's is not possible. So maybe that is a place where to start. Say, okay, suppose there are 3 A's and count. And then 2 A's. By the way, if you have 3 A's, then exactly the same argument will be for 3 B's, 3 C's, 3 D's. So you just count the number of A's, the number of ways this can happen, multiplied by 4. The same thing with 2 A's. All right, so let's start there. Okay, we saw that you cannot have 4 A's. So let's take the 3A situation. 3 of one letter. That's what we're going to count. There are 6 spaces, so we'll say exactly 3. Of one letter only, maybe. Okay, I don't want 3 to. We'll count that separately. So you've got 3 A's. Let A be the letter. So I'm going to count 3 A's. Now, I can't have. Let's fill in the first letter to be A. We need 2 more. I can't put the A next to this. We have to put an A here. Can't put the third A there. And then a B goes in between. So these 3 A's, they have to be spread out, and you have the 2 B's in between them. That already takes care of 5 symbols. right? The last symbol, right? We said that only one letter. So the last symbol could be either C or D. You've got four symbols, A, B, C, D, four letters. Okay, now let's have a look at this. You could have the C placed anywhere. Drawing all these neat things takes too much of time. So let me just draw up one. So you can put the C, for instance, you can put the C anywhere. And then you have to put here, you have to put A, B, A, B, A, B, A. All right. Now the C can be placed in any one of five places. Right. So uh, you then any one of six places at least. So you could have A, B, A, B, A, A, B, and so on. So in this case here, there are six possibilities because the C can be placed in anywhere, any one of six places. And for each one of them, you can fill in the remaining five with that. Okay. So that is if three of A are there. Now, you could have had, instead of having, oh yes, instead of putting C in that last place, you could have put a D, right? So if C is the remaining one, you got six. Remaining letter, you got six possibilities. And also for D. So that makes 12 altogether. All right. Six for C and six for D. Now that is where the A is the one which is repeated. Okay. Now, so for each of AAA, BBB, three Bs, three Cs, three Ds, you can do they have exactly the same argument for any one of these. There are 12 possibilities. Okay, so therefore, altogether, it's 12 times 4 equals 48. Okay. Now, you could have had three of one and three of the other. You could have had that. Like, for instance, you could have had so in that case, you'll have a thing like this: A, B, A, B, A, B. Right? Then you got three. The last letter there I chose it a C or D, but suppose the last letter was like this. Then in that case, what you've got is could have had this, so AB, or you could have had BA, 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 right? And that will give you two different. So for just AB, A and B, you have two. If the two, if the last letter was B, right? Or you could have had three C's and three D's. You could have had CD, 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 and then you could have also had DC, DC, DC. So that makes another two. Okay, now these were not counted in the earlier ones. And this is the only situation where you could have three of one and three of the other. The one will have to be A or B, and the other one will have to be C or D. Right. So those are the only ones where you got 3 plus 3. I can't have 3 C's and 3 A's. That's impossible. Right? Because the other one, if I got 3 C's, the other one has to be a D. So you got only you got 4 here. So therefore we got 48 plus 4 so far. I'm going to put a ring around that to know that okay, now this is the case where you got 3 of one letter. And we still have to look at the case where you got I don't think, remember we got 52 altogether at the moment. Now we have to take the case where now you only got 2 letters. Exactly 2 of one letter. So you don't. In other words, we are saying we are not counting only one of one letter. It's impossible that you could have all the letters only used once because there are six slots. So some letter has to be used twice. All right. So suppose the letter is A. Right. So A is used twice, and therefore there must be a B in between. Right. So your 6 slots here, you've got an A, you got a B somewhere, you got an A like that. Okay. Now, because you got 3 slots here, so what can go in these 3 slots? You have to have C and D. You'll have to have one of the other letters repeated. See? You have to have one of the other letters repeated. You can't have 2 of one and no other letter repeated. Right? Because no matter if you have C and D, you only got 3 places, you see. All right, so the conclusion is that 2 letters are repeated in this case. Right. Now, suppose the letters are A and B, are the two letters that are repeated. Then, what do you have? You have that these will be occupying 4 positions. Now, the remaining 2, how can they be placed? Okay. So you got A, B. Like that. See, you got 2 A's and a B in between, 2 B's and a A in between. So you have A, B is your sequence. Okay, or you could have BA occurring in that order. All right. But now, what goes in here? You can't put another A or you can't put another B. Right? So you can only put C and D in the remaining spots. Right? So what's interesting is that you have to only choose C and D. Put C and D wherever you feel like. You can put C here, you can put D here, for instance. Then you can put AB in the remaining positions, or you can put BA in the remaining positions. So in this positions here, there are 2 possibilities. So we have to see how many ways can you choose, put the C's and the D's in this slot. See, C can be slotted into any one of 6 spots, any one of 6 we call them squares. And once you put in C, then D can be put in anywhere else. You can put D next to it, no problem. Because I'm only using 1 C and 1 D, right? And then D is 5. So the answer is number of ways in which C and D can be placed is 6 times 5. So once you place C and D, for each just choice there is 2, right? So 30 times 2 equals 60 altogether. The crucial ones are A and B, in the sense that in the rules, actually, I'll just withdraw that. Okay, now if you take A and B, now let's take C and D. The same for C and D. The same arguments. Because then you could have 2 C's, namely 2 C's, 2 D's. And 2 D's. Just like as we had 2 A's and 2 B's, and there we've got 60. All right, so at the moment now we have to clear all these lines. Thus far, we have 48 plus 4 plus 60 plus 60. Here you got 3 of each. And here you got 2. But we haven't finished with the 2 yet, because we only considered A, B, and C, D. These are for A, B, A and B repeated, and C and D repeated. Right. But you could have had, you see, if you want to choose two from four symbols, you can choose AB or AC or AD, or you could have BC, BD, or you could have CD. Right. We saw that in these two cases, we had 60. We have to look at AC now. Okay, so what have you got here now? You got two A's and two C's. Okay, I'm going to put two A's and two C's. Okay. Now, I just want to hold on with this. If I got two A's, then the B can be anywhere in between, like this. But I've got two C's. The two C's can only be put in one way. Once I choose A, B, and A, the C, D, C will have to be exactly in that position. The two C's will have to be here and the D's, yeah. In other words, every time I choose a ABA, there's only one way in which I can put the two C's and the D, right? I think that should be clear. Like for instance, if the B was here rather than there, then I'll have to put C, D, C like that. Can't put C, C here, right? So in other words, in this case here, I only simply have to count two A's and two C's. Just count the number of ways AC can be placed. I'm sorry, AB. AB can be placed. See, now here you got two A's and two C's. As I said now, the two A's you'll have to have a B that goes along with it. And once you put the B, you got the C's can be placed only one way. So I might as well just count the number of ways in which the two A's and the B can be placed. Now there are 6 spots. We'll call the spots 1, 2, 3, 4, 5, 6. All right, now you can put the two A's in 1, 3, or you can put the two A's in 1, 4, the two A's in 1, 5, 1, 6, or you can put the two A's in 2, 3. Oh, no, you can't put it in 2, 3, right? Because the B goes in between. You put 2, 4, 2, 5, or 2, 6. And then the A's can be put in, that's 2, starting with 2. You could have 3, 5. You have to put the A's here. You can't put the two A's in 3, 4, or 3, 6. All right. And then starting with 4, you can only put 4, 6. All right. So you got, now in this case here, the B can be put in only one place, in the second position. Here, the B can be put in 2 places. You can put it in 2 or 3 in that situation. Here, I could put the B in any one of 3 places, 2, 3, or 4. And likewise, 4 places here, 1, 2, 3. And here I have 1 and 2. And here there's only exactly 1. All right. So if you work out all these, you get add 10, 16, 20. So there are 20 ways in which two A's and two C's occur. Right. So there are 20 in this case here. Likewise, there'll be 20 here, there'll be 20 here, and there'll be 20 here. They all will count the same way. Okay. Now, so this is the case where you got exactly two of any one occurs, and you can't have exactly one of any one because you got A, B, C, D, and the world will be a situation where you've got at least two of the same kind. You could have three of the same kind. You can't have four. So you can only have two of the same kind, three of the same kind. And we've exhausted all the possibilities for those two situations. So we have nothing else to count. So you've got, the answer is 48 plus 4. There were two 60s and there were four 80s, four 20s. And that gives you 252. So this is an example of counting. It can be quite tricky. So the moral is you separate the issues. Yeah, I said four of one kind, three of one kind, two of one kind, one of one kind. You eliminated the first and the last. You only had two cases. And then we take each case separately and count them. But you have to be, very careful the way you count them. All right, so let's get on to the next problem. Okay, so here I write down the solutions in detail. So you can have a look at that. And this too, this is the same thing that I had, the little table at the bottom there. I did that one. And at the end, we say, as you can see, there are 252 such sequences. And that takes care of that. So now we go to problem 3. Oh, this is a geometric problem. The problem says ABC is an equilateral triangle, and D is a point on the line segment AB. So we choose a random point on that line segment. So you got an equilateral triangle. Oops. All right, this is ABC. And then a point D is chosen on AB. Let's put AB at the bottom. So D is chosen somewhere. Now let E be a point such that ADE is an equilateral triangle, but E and C are on opposite sides. So you got C is on opposite sides of AB. There's AB. So you want E to be downstairs. And ADE is an equilateral triangle. Says that such that ADE. So it's a new equilateral triangle which is constructed downstairs. So this is another equilateral triangle. Okay. And this triangle is called E. Now they say let F be the intersection of CD and BE. So you got CD Okay, CD, it needn't even be a line segment. When they say the line CD, it means the line that goes through C and D. So CD and BE, like that. So F is this point here, where these lines meet. Okay. Prove that F lies on the circle through A, B, and C. This F, where these lines meet, prove that they lie on the circle where there's only one circle that can go through A, B, and C. Right? For any triangle, there is a unique circle that contains the three vertices, and the center of that circle is where the perpendicular bisectors of the three sides meet. Okay, but but there is a circle, and prove that F lies on that circle. And they also prove that F lies on the circle through A, D, and E. In other words, these two equilateral triangles, if you draw their circles, show that F lies on both the circles, in the intersection of those two circles. Okay, so let's do this problem. Sorry, this whole thing shifted. Okay, let's go to this one. Okay, we can see that EB, F is where EB and CD meet in this diagram. So this is where we are. Now, when we analyze this, I want to show that these points, A, B, C, that's the equilateral triangle, vertices, and this new point, they are concyclic. In other words, they lie on the same circle. So that's the goal. Right. Now we know that we have two equilateral triangles. And now I've actually shaded two triangles. You can see I've shaded this triangle here. This triangle, one of the sides is the equilateral side, the large equilateral triangle side, and the other one is the small equilateral triangle side. We should have had the equilateral triangle was something like this. Right. So the purple triangle has got a side of the large triangle and as well as the side of the small triangle. The yellow triangle, this is a double stroke because this is an equilateral triangle here. And the other side of the yellow side is again the side of the large equilateral triangle. So these two triangles, I've got two of the sides are the same, right? And the angles between the sides, here the angle is 60 degrees because it's an angle of the equilateral triangle. The angle between these two sides is also 60 degrees because this small triangle is equilateral. So the point about this is that the yellow triangle and the purple triangle are congruent. The reason for congruency being two sides and an included angle. Okay, which means that all the properties of the purple triangle are shared In particular, suppose I take this angle here. This angle in the purple triangle. Let's call it X. Now that is opposite double stroke in the purple triangle. And the angle opposite double stroke in the yellow triangle is that one. Now this is very nice because if you look at this thing carefully, you'll see that these two angles are now equal. They are both subtended by this dotted line. See this dotted line? If you start from here, you go up to C and you come back here, you'll get X. And if you take the dotted line, you start from C and go up to B, come back to F, you'll get the same X. So they're both subtended by the same line. So this theorem in geometry says that if you got a line segment subtending equal angles at two other points, then these 4 points are concyclic. Or in other words, the points, you use the word concyclic for points and cyclic for quadrilaterals. So these 4 points are concyclic, which means that, which is the same as saying that ABCF is a cyclic quadrilateral. And that is what we were required to prove. Okay, but we also, so F lies on the circle that goes through A, B, and C. Right, so we also needed to show that F lies in the circle that goes through A, B, and D. Okay, now we took this to be X. Why don't we look at the other angle, or maybe this angle here. Now, this angle is opposite that stroke there in the purple triangle. And the yellow triangle, the angle opposite the stroke, it'll be AB because ABC is the equilateral triangle. So this will be a stroke here. Angle opposite stroke is this one. So these two angles are equal. But now, interestingly, if you look at this quadrilateral, that one, you will see that Y is an external angle or exterior angle of this quadrilateral, and it's equal to an interior opposite angle. This is another theorem in geometry, which says that actually, I think the theorem says that if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. So you can see this angle plus this angle is the same as that plus that, which makes it supplementary. So this quadrilateral here is cyclic, right? Which means that these 4 points are concyclic. 3 of them are the 3 points of the equilateral triangle, the small equilateral triangle. So therefore, F lies on the circumscribed circle of that equilateral triangle. I actually drew drew 2 equilateral triangles, and I drew the circumscribed circles and all this figure, and to see whether those 2 circles actually intersected. And you will see here. See, I've drawn the circle to A, B, and C. I've just drawn a part of it. That's a green circle. And here I drew a circle which goes through A, D, and E. A, D, and E. I drew that circle. And you notice that both the circles contain F as advertised. But if you draw it, if you construct it, you'll see it goes. But we've actually proved it using geometry. Okay, so that takes us to the next problem. This is problem number 4. Problem 4 says define the sequence A1, A2, and so on. First term is 2, A1. And for numbers bigger than 1, you got rules which tell you how to find the how to find oh, why doesn't this work? Okay, how to find the n plus 1th term. If the nth term, the one just before it, you see the an occurs 3 times, yeah, and n are known. So if you have n and an, then you can work out the n plus 1th term. Now, this is sort of a sort of non-traditional kind of a problem. Usually, what they do is they give you a a method of finding out the n plus 1th term in terms of the previous one, maybe an squared or something, right? Then each time you have a term, then you can find the next term. See? So there is some rule. Sometimes it might be not just the previous one, it may be like the Fibonacci sequence tells you this, the sum of the 2 previous terms. But the point is that any given term is usually given in terms of the preceding ones so that you can construct a new one, step by step. But this one here is a little bit awkward because it also, the symbol n occurs in the formula. Usually this doesn't occur. See? So therefore, both n and an, the position of the sequence, the term in the sequence, together they create the n plus 1th term. So if you want to work out, given this pair, to work out the next an, then what you do is you test 3 ways. You test whether n plus an, whether the sum of these two is divisible by 17. That's one way. And if the product n times an, I'm sorry. The second condition is that if you subtract 1 from the previous term, that is divisible by 17, then you got another rule. And then you got a third rule if neither of these are satisfied. So if the 2 conditions are an is divisible by 17, and if the one just before that is divisible by 17, then you have a way in each one of those cases. And of course, if neither of that works, then you got another rule. Okay. How do you go around doing a problem like this? Looks very, very complicated. But there's one important thing here, that it's all about divisibility by 17. Now, there is a whole area in number theory which deals purely with divisibility. And that area is called congruences. If you got a copy of my book called 1000 Mathematics Olympiad Problems, this book is quite a voluminous book. It's got 643 pages. It's got 1,000 problems together with the solutions and a lot of lessons, which are useful to solve Olympiad problems. So the theory is also given. There's a whole chapter, I think, on congruences. So go to the chapter, and then you can read everything about congruence. We don't have time to talk about that here, but basically what it means is that you got two integers. If you got any two integers, and you fix an integer, say like 17 in this case, right? Then you say that those two integers are congruent. You use a symbol A and B, like an extended equality, right? Extended equality. And you say they're congruent. And the symbol is modulo. A and B are congruent modulo 17. I put a 17 down here. If the difference between A and B is a multiple of 17. Okay, so this has got a lot to do with remainders, because if I divide, say, 59 by 17, then 17 times 3 is 51. So this is 3 remainder, 8. So according to this thing here, 59 minus 8, that's 51. So that is a multiple of 17. When you're dividing, the remainder is always congruent to this 59. And these remainders can only be one of 17 numbers, 0, 1 up to 17. If the remainder is 0, then it means that 17 goes exactly, the 59 minus 0 is, oh, whatever number is here. Let's go here. If the remainder was 0, so in place of B, I can put R, where R is the remainder on division by 17. If R was 0, then A is a multiple of 17. And if R is 1, then AN minus 1 is a multiple of 17. So you can see these things here can be translated into, this is N plus AN is congruent to 0, 117, the first one. And the second one, AN is congruent to 1, 117. So the idea is just to simply divide by 17 and take remainders. And you work only with remainders, because this problem here is all about remainders and divisibility. So you work only with remainders. So the question now is, you've got a pair NAN, and for each number, you can calculate the AN plus 1. But we will only put the remainders here, because we need to calculate the remainder when the 2003 fifth term is divided by 17. So I'll calculate the remainders, and in each of these cases, another complicated sort of rule, but I've actually calculated this. So what we did here was, okay, so these are the three rules. I'll put it right at the corner, and I've calculated for N and AN. So when N was 1, A1, this is then A1, N equals 1, it was given that it's 2. Right. So this is given. Let's just look at the first view to see how this table was constructed. Now I'm looking at A2 now. Right. Here, This is your an plus 1. So n is 1 in this case. A to n is equal to 1. So you have to look at 1 plus a1. Well, you have to look at whether a1 is divisible by 17 or whether a1 minus 1 is divisible by 17. And if, in either of these cases, you got two rules. And then if neither of these rules are satisfied, then you use the third one. Okay, so in other words, I take 1 plus a1. This is your, I take 1 plus a1, 1 plus 2, right? No, I'm sorry. We want to find out whether this 17, is it divisible by, is 2 divisible by 17? No, right? If is 2 minus 1, namely 1, is that divisible by 17? No. So therefore, the third rule kicks in. So it will be a1 squared, right? And a1 squared is 4. This is a1. All right, so the third rule kicks in. Now, let's look at the next one now. Now, you got your n and you got your a, you got your 2, a2, n equals 2, and this is your a2. Okay, now we look at a2. Is it divisible by 17? No. Is 3 divisible by 17? No. So the third rule kicks in. So the third one will be 4 squared. So an squared. Right, now again, you ask the same question. Is this divisible by 17? No. Is 16 minus 1 divisible by 17? No. So the third rule kicks in. So this becomes 256. 16 squared. As I said now, you write down the remainders. See? On dividing by 17. Now, otherwise, these numbers become very clumsy. You wouldn't be able to, unwieldy is the word. Now, when I divide this by 17, so 255 is a multiple of 17. You see? So, therefore, the remainder is 1. So an minus 1. So this kicks in here. An minus 1, which is 256, minus 1, which is 255. Right? Now, that is divisible by 17. So therefore, the rule that you use here is n times an. So it is this times this. 4 times 256, actually. Right? But that will be 4 times 1, which is 4. You see, the interesting thing here is that this congruences has got very powerful applications. Because when you divide 4 times 256 by 17, right, with 1024, the remainder is 4. It's exactly the same as the remainder when you say 4 times 1. So in place of 256, if I put a 1 there, then 4 times 1 is 4. So I still get the same remainder. See? So therefore, instead of multiplying 4 and 256, I'm simply writing around remainders. Yeah. So the remainder is 1. So that's how the next one will be 4 times 1, which is 4. So the fifth term is 4. Now let's do one more. 17. No, you'll notice the first two are kicked out, but it now comes to 16. And 16 we saw gives you 1. And here now, the next term will be you have to multiply these two together. The remainder is 1, and that rule kicks in. So this becomes 7, right? And now when you look at this, and you look at subtracting 1, something, neither of the first two kicks in. So it's 7 squared. Now 7 squared is 49. 49 is 34 plus 15. When dividing by 17, the remainder is 15. So this is how all these remainders are got. Now you'll see I went all the way right up to quite a lot. Why did I do all this? Because I want to work out the 2025th term. So I want to work out A2025. And we saw in most of these problems, so-called iterative sequences, the trick is to see where you got exactly the same thing appears twice. The moment the same thing appears twice, then the rest of the strain here will continue to recur. The word is recur, right? So, and then once you got that, then you've got a way of calculating this thing here, which is so far away. So I was trying to see whether the pair, because it's NaN, that's your pair, which will create the new term. But when you went right through, you see you got 7, 1, but this is 12, 1. That didn't help too much. Now, when I came to 17, I replaced 17 by 0 because that's the remainder when you divide by 17. I want all the things to produce the N and the AN to be reduced to the remainders. So the next one, this is 18, by the way, and 34, this one here is 0, and so on. And so I wanted to see where these things are repeated. Here I've got 4, 1, 12, 1, 2, 1, 6, 1, 11, 1, 16, 1. Oh, there's something else. It's hidden here. Actually, the 36th one, 34, 35 is 1, 1. Okay, so when the remainder is 1, so this is your AN. Now you'll notice that AN minus 1, which is 0, is divisible by 17, right? So you're going to have the next term is going to be the product of these two, be 1 times 1, right? But then also, (16 plus 1), you see the previous one, is divisible by 17. So the first rule kicks in. So this becomes the next term is n plus an. So it will be 1 plus 1, which is 2. See? So the 35th term is, actually the 36th term is 2, 1. This is the 35th term. 36th term is 2, 1. That's missing. And you will see that is repeated. That's 2, 1. So that is why we had to take such a long time, because the repetition wasn't coming. The first time it repeated was on the 36th term. It made you calculate these things for so long. Anyway, so what happens is you've got the 17, 18, 19, the 19th term and the 36th term are both equal, right? mind you, see, the fourth term is equal to this fourth term as well, but we can't make any conclusion from that because you got different ends, you see. You have to have n and an to be the same, right? So this thing repeats like this. Then you'll see 19 and 36, the difference is 17. So after every 17 steps, it repeats. So you have, if you add 17 to that, you get 53, and so on. So when you come to A2025, right? Now this is, if you divide this by 17, the remainder is 2. If you divide this by 17, the remainder is 2. If you divide this by 17, the remainder is 2. And if you divide this by 17, right, you will see that the remainder is also 2. So this is actually equal to, so A2025 is the same as A19. And A19, as we saw, is 1. A17, A8, 19. So A2025 is 1. Well, actually, the remainder. We need to calculate the remainder when A2025 is divided by 17. So this involved congruences. You might not have been very familiar with them, but if you are going all the way to the third round of the Olympiad or the International Maths Olympiad, I suppose they expect you to know something about congruences by the time you reach there. The congruences is very nice. Instead of multiplying A and B, you just multiply the remainders. And when you divide by 17, you get exactly the same kind of a result. Okay, but I'm not going to go into detail with that. Okay, so let's just expose what I had written. So I write down each new term of the sequence is obtained from the previous pair once. So we are concerned only with the remainder divided by 17. So we reduce all to modulo 17. I explained what you mean by that. Modulo 17 means divide by 17 and find the remainder. And that is what the new number will be replaced by. I also argue that the n and the an, 17 ways of choosing, so n and the 17 ways of choosing an, because we're only using remainders. So there are 289 distinct pairs. Right? So therefore, there will be repetition. Right? If you keep taking work, there will be a repetition. So we concluded that there will be a repetition, but not only that, we actually found out where the repetition occurred. It took a long time, but we eventually found it. Anyway, that is, and this is exactly, or even here, that 2-1 is missing. 836, I only go up to 835. All right, so you can see the last sentences. The remainder is 1 when A225 divided by 17. That's the same conclusion I came to. Okay, so let's get to the next problem, which is problem number 5. Problem number 5 says, show that there are infinitely many functions. F. Z is the integers. Positive and negative integers, positive integers, negative integers together with 0. And it says that if whenever you have that these three integers satisfy this equation, you have some complicated formula which is satisfied. Right? But you must show that there are infinitely many functions which allow this to happen whenever you have that condition satisfied. This condition is satisfied. Now, look, by the time you get to problem 5, problem 6, these problems become decidedly difficult. So this is quite a complex problem. So let's write down these things. I have to confess that it took me a very long time to unpack this problem. So listen very carefully. Okay, I want to first observe that x, y, z, if I choose x, y, z to be x1 minus 1, or for that matter, in other words, two of them are minus 1, then you have that, so you have x times 1, y is 1 times z, xy plus yz plus zx. This is plus minus 1 times x. Now this, if you simplify it, you get x minus 1, and minus 1 times x is minus x, and that is minus 1. So it satisfies, right? So no matter what x is, this triple will satisfy the equation, which means that no matter what x is, that this equation will be satisfied. So f of x squared, now y is 1. So you have f of 1 squared, and z is minus 1. Minus f of 1 times f of minus 1. I'm sorry, f of x. F of 1 and f minus 1 is equal to 4. All right, let me give a name to f of 1 and f of minus 1. Give two names. Let f of 1 be equal to a, and f of negative 1 equal to b. And this is very cumbersome, like this. Then it means that you got f of x squared plus a squared plus b squared minus ab times f of x equals 4 for all values of x. All right. Now f of 1 is a fixed number, f of minus 1 is a fixed number. Okay, so what I'm going to do now is, since this is true for every value of x, so let x be equal to, let's call this equation 1. Let x equal to 1 in equation 1. Then you'll have f of 1 squared, but f of 1 squared is a squared. So you have a squared plus b squared, and you got minus ab, and f of 1 is a again. and that is equal to 4. So if you simplify this, you got 2a squared plus b squared. This is minus a squared b equals 4. And if you substitute 1 in that equation, this is what you get. All right, now I'm going to, this is supposed to be, let x equals 1. Why did I write this? This certainly doesn't look like an x. Right, so when x equals 1, I have this equation. But I could put x equals minus 1 also. And in that case, the same equation 1 right at the bottom there, you can see it. So now you have f of minus 1, x is minus 1, but f of minus 1 was b. So now you have b squared plus a squared plus b squared minus ab, and f of minus 1 is b. That's still equal to 4. See, we can use this because these numbers satisfy the condition. So we are allowed to use this. We can't, this is not always true. It's only when that is satisfied. Okay, so this time you have this equation a squared. That I'm going to write down at the bottom. You got 2b squared. And then this is minus ab squared is equal to 4. Now, we don't know what f of 1 is, f of b is. But now we've got two equations involving a and b. In other words, we've used the conditions here to actually get two equations involving a and b, which means that we might be able to actually work out what f of 1 is and what f of negative 1 is. And that is what we are going to try to do now, using these two equations. Well, you aren't ever seen equations of this type, but because since we got 4 on both sides, and normally equations, you try to get to 0 somehow. Let's subtract them, and then you have a squared, 2a squared minus this. This is minus b squared. And then you have minus a squared b plus ab squared equals 0. Right. Then you notice that this is actually factorizes a minus b into a plus b. Here you have plus ab, make it minus ab into a minus b equals 0. Minus ab into a minus b. And therefore you have a minus b into a plus b minus ab equals 0. All right, so we still haven't worked out what a and b are. Must be very careful that I don't wipe out everything. Otherwise, I have to reconstruct. Otherwise, I have to reconstruct all these equations, which I'm not very. I might need this little equation here. Okay, so what do we have? Now, the conclusion from this is that either a equals b. When you have two numbers multiplied to give you 0, then one of them must be 0. Or, not both, or a plus b minus ab equals 0. All right. Okay, so now if a is equal to b, I suggest that even here you have that A is equal to B because yeah, this is very interesting. Yeah? If you this kind of a thing, there's always a very neat little trick that you can use. You see, A plus B minus AB is equal to A plus B into 1 minus A equals 0. And then so B into 1 minus A is equal to minus A. Mm, yeah, actually, what I want is, let's just take, I'm trying to get a common factor here. And I think I'd rather write this thing down as A plus B minus A. Uh, sorry, let's make this thing A minus A into B minus 1. Right. Now we had that all this is equal to 0. Okay, so no. So this is B plus. This is B plus. Sorry. Okay, now the trick is you subtract 1 from both sides. Zero minus 1 gives you that. And then B minus 1 is a common factor on the left-hand side. But this is equal to minus 1. See? Now these are integers, right? And when you got two integers being multiplied to give you negative 1, there's only one possibility. You can have B minus 1 is equal to 1 or minus 1. The letters, the factors will have to be either 1 or minus 1. Those are the only factors of negative 1. And this will give you B equals 2 or 0. B minus 1 equals minus 1 gives you B. Now B equal to 0 is not allowed simply because if B equals 0, then you'll see oh well, anyway. Okay, if B is equal to 2, then A and B are both equal, right? So therefore, oh, no. A and B are not equal in this case. If B equals 2, B equals 2, and then if B equals 2, then 2 minus 1 is 1, is 1. You have 1 minus y is minus 1. You have A equals 2. I want you to put B equals 2 here and calculate A. And here, if you have A equals B equals 0, you have minus 1 here, and the minus 1 cancels with this, and you will have A is equal to. If B equals 0, then you have minus 1. 1 minus y, A is equal to minus 1. you have a is equal to 2. Okay. Now, so you could have this situation, but you have that A and B are equal, right? Even here. Or you have AB equals 2, 0. All right, so you have that. Let me take all this out. I'm going to clear everything. So in this thing here, you have A equals B. We saw that A equals B equals 2, or AB is 2, 0. Right? So that may be a possibility. I don't know. I discarded the second possibility, but I can't recall why. Okay, so now if A is equal to B, remember you had A squared, 2A squared plus B squared minus A squared B is equal to 4. I think we have something like that. Now, if A is equal to B, then you have two A squared plus A squared minus A cubed equals 4. And this implies that A cubed minus 3A squared, bring it to the other side, plus 4 is equal to 0. And here you got a cubic equation. And one of the ways of solving a cubic equation is using the remainder theorem. And I trust that you know what the remainder theorem is. You substitute various values and see whether the answer is 0. When you work out -1 all cubed minus, you substitute -1, then you have -1 plus 4 is 3, minus 3 is 0. So A equals -1 gives you a solution. So therefore A plus 1 is a factor. And when you factorize this one here, you will see that you have A minus 2 all squared equals 0. Right? When you work out the other factor, you'll see you get A squared minus 4A plus 4, which is A minus 2 all squared. So therefore, we're now zoned in on what the possible value of A is. A is equal to -1, or A is equal to 2. So that is the whole purpose of this investigation, was to find out what is f of 1 and what is f of -1. So we have that A is equal to B, so you have that f of 1 equals f of -1, A equals B, or f of 1 equals f of -1 equals 2. All right. Okay, let's just take the case where f of 1 equals, where this is true. Okay, suppose f of 1 equals f of -1 equals 2. Then I want to calculate any f of x, or for any x. We had the equation f of x squared see, earlier on we had f of x squared, and here we had plus a squared plus a squared. So you got plus 2a squared, and here you have minus a squared f of x times, I think, minus a squared f of x equals 4. Now, a is equal to 2. In particular, if x equals 1, then you have I wrote this thing out, so I can't remember what I had here. I had ab here, so minus a squared f of x. Now, that's quite right. Okay, so you have something like this. And now we had a is equal to 2. So you have f of x all squared, a equals 2. So you got 4, 8. Yeah. So you have minus 4 f of x. A is equal to 2. And then 2 squared is 4. 4 2 is 8. 8 minus 4 is this. Plus 4. And now you see that f of x is a solution of a quadratic equation. And the quadratic equation is f of x minus 2 all squared equals 0. So therefore, f of x is equal to 2. Now, so for any x, f of x is equal to 2. And here we said f of 1 and f of minus 1 is equal to 2. So this becomes a constant function. Right? So in this case, we are led to the constant function. It's quite a long discussion to get to unpack this problem. So here you have that but the problem is to find infinitely many value functions f. We found one now. Right? If f of x is equal to 2 right throughout, you'll have 4 plus 4 plus 4 minus, that's 12, minus 2 times 2 times 2, which is minus 8, is equal to 4. So this is one of the functions which will satisfy this equation. So we're not really interested in this function. We want to find infinitely many functions, right? So let's take the other case here where a is equal to minus 1 is equal to b. That's the other one, right? So what happens in that case, if I go back to the same equation, now a is equal to minus 1. So we had f of x squared plus 2a squared minus a squared f of x equals 4, the same equation. A is equal to negative 1. So you have f of x plus 2. A is negative 1. F of x. Right? A is negative 1. And then you have another quadratic equation. And this time, this quadratic equation factorizes like this. F of x is either equal to 2 or f of x equals negative 1. All right, so now at this point here, how do we interpret this thing? What we are saying is that this condition that we have had, it eventually led to a situation where the function can have only two possible values, either 2 or negative 1. Right? Only two possible values. So what I'm going to do is now look at all the situations where f of x is either equal to 2 or is equal to -1. And I got it in this table. So you'll see here, the f of x is either equal to -1, all of them -1, or two of them -1. This is, maybe I should put grid lines here. I couldn't get grid lines in my using math type, which I use. All right, so the first case is where all of them were -1. Second case is where two of them are -1. The third case where one of them is -1. The last case where none is -1. So we've taken all possible cases here. And in all these cases, then I calculated the product, right, of these three numbers, as you can see. And then I calculated S, which is this thing here. And I wanted to see whether it's equal to 4. And I found, quite surprisingly, well, not really, but we found that in all cases, this final condition is satisfied. Now, remember, I'm not worried about whether x, we're not worried about whether xy plus yz plus zx equals -1. Regardless of that, this is what we have. So in all cases, it happens like, except in this case here. This is the only case where the S is not equal to 4. We wanted it to be equal to 4, you see. That is the conclusion. So all we have to do is to avoid the possibility that there are two 2's. And if you got two 2's, then it doesn't work. If you got 1, 2, or 3 2's, it works. And so I try to avoid the possibilities of two 2's. Now remember, we are trying to find infinitely many functions, right? And the value of the function is either 2 or -1. Okay, so to avoid two 2's, make everything equal to -1. Let f of x equal to -1 for all values of x except 1. This is for all values. Upside down A. For all values of x except 1. In that case, you will have that this condition is satisfied. So now that gives you infinitely many functions, because you could take, for instance, you can take 13, for instance, and send it into 2, and all the rest you send it to -1, right? When n is not equal to 13. Right? So this will give you one of the functions. This function here we can call f subscript 13. Right? So for each integer, which is different from 1 and -1, so this gives you a possible function. Like this, now the 13 was just randomly chosen. So you can see that I have infinitely many functions, which will satisfy this condition. Well, quite a demanding problem. And I hope you understand it. But let me just show you all my calculations. Okay, that's a question. That one. Right. So here's the full argument. That's the first page of the argument. The second page of the argument. Oh, I don't know, all these things got knocked out. It's on my screen, but it's not here. Anyway, you can do the calculations. And then I'll finally say how to construct the different functions. So right at the end, you can say for each n different from 1 and -1, let fn be the function that sends n into 2, like 13 into 2 and the rest -1. And all such functions satisfy the given condition. Okay, so that takes me to the last problem, which is problem number 6. So let n be a positive integer. We say that an n by n grid of integers is good if it contains the integers from 1 to n squared exactly once. Okay, so if you have an n by n grid, okay, let me just take, for instance, the 3 by 3 grid. So there are 9 symbols here. It contains the symbols from 1 to 9 exactly once each. So you can put 1, 2, 3, 4, 5, 6, 7, 8, 9, for instance, right? Now, for each row, the largest number in that row is also the largest number in that column. Right? And here you can see the largest number in this row is 4, but it's not the largest number in that column. So this grid, this 3 by 3 grid, is not good. Okay, so there's no word for not good, by the way. Don't say it's bad. You can use it. Anyway, so now the question is now, how many good n by n grids are there? Okay, so what I'm going to do is I'm going to try to construct these grids. So suppose I want to construct a 3 by 3 grid. Let me make it look somewhat neat. Actually isn't. All right. So how do I construct it? Well, I take the very largest number first. In this case, it'll be 9. And I'm going to put it anywhere in the grid. Like there. Right. Now, that 9 is going to be the largest number in that column and also in that row, in its row. Right? Obviously, it's the largest number in the entire grid. Now, what I'll do is I'll eliminate the row and the column in which this occurs. Now I have 4 numbers. And now I take the second largest number, which is, actually I don't have 4 numbers. Yeah, I take the second largest number and choose it anywhere inside this. Right? I'll choose the second largest number anywhere in this smaller grid. If I choose it here, for instance, right, then you have this situation. Yeah, then the third largest number will have to be here in this 3 by 3 grid. And in this situation, you can see 8 is the largest in the row and the column, 9 is the largest row in the column, and 7 is the largest row, because these are the 3 largest numbers. All the other numbers are smaller than that. So bearing that in mind, if you have an n by n grid, so the first thing to do is to choose your largest number anywhere in the grid. You've got an n, not a 3 by 3. The largest number can be chosen in n squared ways. We said anywhere. Right. Now you have to choose the second largest number, n minus 1. No, it's n. Yeah. We're not mentioning what the second largest number is, but that number is n squared minus 1. Right? We want to find out how many ways can that number be placed. Now, if you notice here, you've got 9 squares and 5 have been eliminated. So there are 4 choices, as we saw, for the second largest number, and we chose that one. We could have chosen any one of those 4. Chosen it there or there or there. And then the third largest, okay, let's do that. So the question is now, how many squares remain when you choose the second largest number? So originally you had n squared, and you're going to eliminate the row and the column in which that occurs. You've got n here and n here, which makes 2n, but don't count that. So it's 2n minus 1. So this is what remains. Number of. And this is n minus 1 all squared. N squared minus 2n plus 1. And we saw 3 minus 1 is 2. 2 squared is 4. Right. But now, if you keep going down like that, what happens? How many remain? So a much better way of looking at it is to, you see, if you got the largest or any one particular square, so suppose this was where the largest occurred in any particular step. Eliminate this, and we want to know how many left. And I see that to find out how many left, you don't have to do much of a count. All you do is you shift this to the extreme right, and shift that one to the right of the top of the column, right? And you will have exactly the same squares, and this, yeah, and the number which you're going to take out this. You see, there's one square which is common to both here, and here too there's one square common to both, right? And it'll be the same count. So you're going to remove this from your n squared, and you're left with only the white squares, see? And that becomes a new square with sides n minus 1, right? So you choose the first number, the highest number, in n squared possible ways. The second one can be chosen in n minus 1 all squared possible. You can choose it anyway, right? Now you eliminate the row and the column of that. And again, once more, if you push it to the top, right, you will have the same number of empty squares as this new version. And now you can see it will be n minus 2 all squared. You have to choose the third largest number in n minus 2 squared ways. In our 3 case, we had 9 in the first one, and then you had 3 minus 1, 4, and 3 minus 2 all squared is 1. If you remember, in the 3 by 3, there's only 1 left over. All right. But now you go on like this. So each number can be chosen in so many ways, right? There are n of them, right? Because you're taking the n largest, it's n by n square. The largest one, there will be the largest, the second largest, and so on, and until you come to the nth largest one. So if you had, for instance, if you have 4 squared 16, 4 squared is 16, You choose 16, 15, 13, 14, and 13 to be your largest numbers, right? But there will be only four of them, right? So, so this comes all the way down to 1. So the total, until you come right down to this last thing, and then the number of ways is now quite clear. It's going to be so the number of such grids, number of good grids will be equal to what we did was we tried to construct a good grid, and we saw that the first number can be chosen in n squared way. The second highest, now to take the highest, the second highest can be chosen in that ways, the third highest, and so on, and the nth highest will be 1 squared. So this is equal to, it's actually equal to 1 times 2 times 3 up to n. So uh, oh yeah. Now once you choose the highest, oh yes, yeah. You see, what once you choose this, now what about the others? Now you got your grid, you got the 4 highest chosen, right? And you, as you saw before, you got that is filled, that is filled, that is filled, maybe that is filled. Yeah, it'll be 16, 15, 14, 13. 4 by 4 I got. What about the others? Now you can put whatever you feel like in the rest of the stuff, right? Because this will always be the highest, no matter what the others are. Now, how many are left? You have n squared originally. N numbers have been taken out from there. So the remaining one is n squared minus n. And they can be arranged in any number of ways, right? In all possible ways. And that is n squared minus n factorial. So therefore, the top n can be chosen in that number of ways. And the remaining ones can be chosen in n squared minus n factorial ways. So therefore, the number of grids that can be chosen altogether is n squared is equal to this. Okay, so that is the answer to the last problem. Okay, this was quite a long session. I know you're probably quite tired. Well, let me just show you my solution, and you will see you've got right at the bottom n factorial squared into n squared minus n, and all factorial. Let's realize that this page doesn't show completely. So I have to be careful when I'm preparing my slides. See, okay. So that takes us to the end of this. Thank you very much for listening, and enjoy the rest of the day. Oh, by the way, before you sign up, just one thing. I mentioned this book. I didn't tell you how to get it, but you have to get it in the SAMF website. I've given you the address for that. If you go into that SAMF website and search for the book 1000 Olympiad Problems, right? I'm the author. It's a very good book to get for all Olympiad truth enthusiasts, Prof Pillay. And it sells for a price. You have to buy it. It's either an e-book or a solid, what do you call, hardcover, not hardcover, yeah, uh, non-digital or whatever it is nowadays. I forgot what you name an ordinary book. Um, it'll be one of those, and you can purchase it from the people who actually sell this book. Okay, thank you very much for listening, and bye.